All right, we're rerouting a little bit. We're going to do a family tree of innate and adaptive. So, innate, what goes underneath innate? So underneath innate, we have basically everything that doesn't need to be taught how to do its job. It just does it. That includes, if you remember, there was a tree that, I'm going to draw an actual tree and then I'll draw a list, okay? So if you remember, there was the pluripotent stem cell, which then went down, and you have the lymphoid and the myeloid pluripotent stem cells, progenitors. And then they go down and they differentiate into a bunch of other stuff, okay? And then this one's got, so innate is the stuff on this side, pretty much, okay? On the right side of the tree, if you go back and find that tree, and so we're talking about innate right now. Innate has, right here, there's monocytes, which differentiate into macrophages. I love the fact that he does an M with a, what is that, a psi? I don't remember what the sign's called, but it's so much easier. I'm lazy. Dendritic cells, I'll write that one out. Dendritic cells. And yeah, there are two types of those, but for right now, we'll keep it. Okay, and then we have eosinophils. We have basophils. And let's see. Yeah, neutrophils. And then over here we had red blood cells, which are erythrocytes. You don't need to write these ones down. This is just so that if you go to the tree, it's not like, oh, what are those? And then technically also the megakaryocytes, which I don't think were on that tree, but they go right here. Karyocytes. Sue me if I don't spell right, which would mean a lot of lawsuits. So, these guys are innate. Macrophages are innate, dendritic cells are innate, monocytes are innate, eosin, baso, and neutrophils are all innate. And then there's a little side category here, which is like the lost cousins, and we're just going to call these complement. All right, so here's how I think it might help to try and remember. You have this little monocyte clump. So remember, monocytes, and they're two things, okay? That's one item. Your second item are these ones. They all end in phil, eosinophil, basophil, neutrophil. That's a second item.
Well, if you use neb as the thing, neutrophils
Sweet.
are most populated.
Yes.
Then eosinophils, then basophils.
Nice.
So
you even have
bend backwards.
Yeah. I learned never let Mary eat bagels, and it goes and it covers all of them, including the ones we're not talking about over here. And it's never is neutrophils, let is lymphocytes or leukocytes. I always forget which one's which, to be honest on that. Mary is monocytes, eat is eosinophils, and bagels is basophils. And it's like, dang, I love that. So these three, yeah, so neb, if you want to do it in order, then that's great. That's in order of population. Then over here you have complement, which is also innate. So those are the three things, 1, 2, 3, and then you don't need to remember these ones because they're sort of for other jobs. They're not really immune system cells. They just happen to have the same grandfather.
Okay.
All right, so go ahead and look at it for a sec if you like. When you're ready, go ahead and close your eyes and then see if you can bring up the 3 different clumps of cells and name them.
Okay.
All right.
So monocytes include?
So monocytes, okay, so differentiation, really quick. So differentiation is, here's a monocyte. This monocyte, if it is triggered in one way, it will pull out different DNA, and it will activate that DNA, and then that DNA makes it act like a macrophage permanently forever. It doesn't ever go backwards that we know of. If it gets triggered to pull out different DNA, then it becomes a dendritic cell permanently forever. It doesn't go backwards that we know of. Okay? And so basically this is just specialization. What kind of DNA are we activating? And all the way up here, this thing could become anything. Right now, all of its DNA is available. None of it has been wadded up and stuffed in a corner. And so each of these, if we just said this is a single cell's life cycle right now, we would say, okay, right now this is the cell. It has all of its DNA available. It gets triggered to go this way. Same cell, some of its DNA has been stuffed in a suitcase. And then it gets triggered to go down to monocytes. Some more DNA has been stuffed in a suitcase, and some other is starting to make stuff. It gets triggered another way, and then it finally decides it's going to be a macrophage. That one cell has gone through this thing, and it is a macrophage now. Other cells could take a different pathway if a different signaling molecule or whatever hit them and made them go, oh, I went down here, but now I actually was signaled to go down here and become an eosinophil. And then they just have eosinophil DNA that is expressed, and so it's coded, you make all the proteins, that's what makes you an eosinophil. At the beginning, every cell has all the DNA. What makes a cell different is what DNA it chooses to use. So, monocytes are things that still have options. They can go left or they can go right. They haven't been told which DNA to stuff in a suitcase and which DNA to use.
Okay.
So that's what's going on with this whole tree, is just specialization of DNA.
Okay, and then what's the name of the cell that eosinophils, basophils, and neutrophils come from?
So, to be honest, I don't remember, and I'm not even sure if we really fully... I know that some of this is still under debate. I think we know that one. I think it's called the common... So, it's called common myeloid progenitor. Common...
That's not something we need to know.
Myeloid progenitor. For this test, no. There also might be some other intermediate steps that don't ever worry about those unless someone explicitly tells you to. This one, maybe by the time boards come around, you'd want to know what that is. Myeloid means this half of the tree. Progenitor is, you're good with...
Breed.
Yeah.
Yeah, before.
You know what plethora is and all those other words you're talking about. So really, common means that it has lots of different things. Myeloid, this half of the tree. Progenitor comes before. And so once you don't need to memorize it. Just remember that it exists. And when you read it on a test, it'll be common myeloid progenitor. I know myeloid is that stuff. So myeloid is a code word for innate, almost.
Okay.
So minus these guys. Okay, so the three groups, we have monocytes that have macrophages and dendritic cells. You can remember the two things that come off of there in a lot of different ways. If you need a trick to remember it, you can remember MD. So monocytes want to be doctors.
Okay.
So you can have a doctor monocyte. You already have neb here. And then complement. We really like neb, so we're going to complement neb. And then you have all three of those things and see if you can unpack them. All right. So.
Okay, so from monocytes come macrophages and dendritic cells.
Bingo.
And then the next group would be the neutrophils, eosinophils, and basophils.
Bingo.
And then the next group are the cousins. That's the complement.
Yep. All right. So that is pretty much all the innate cells that I can think of off the top of my head at the moment. Good job. So now let's go ahead and go over here I guess we have room. There's actually not too many of these guys. All right, innate. We go down to, and this one's sort of like that. All right. So, and they're not
So
different
that's
heights.
still the innate system?
Oh, excuse me. Adaptive now.
Okay.
All right. I'll even take the bar away right there. Okay. So in blue is the adaptive. And that means that I'll change this to blue. All right. Adaptive is actually pretty friendly.
Okay.
For all the complicated stuff about this talks to that, and then that talks to that, and this activates that, blah, 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 there actually aren't that many cells.
Okay.
So you have, they're the letter cells.
Okay.
So you have B, T, and NK. They're the letter cells. Okay?
Okay.
Now, B has, B cells we'll get to in a little bit. T cells have a few subtypes, so I'm going to go ahead and put those in. Okay? So T cells, there are 4 subtypes that we care about presently. Okay? So we're going to call this helper 1, helper 2, 17, just T17, TH17, and the other one is Treg. All of these have multiple names. I'll tell you the other names. I'll give you the other most common names for each of those. So helper 1 is, oh, excuse me, hang on. Let me make sure. This is right so far. I'm just making sure the names I'm about to say match up properly. Okay, great. So H1 has the other name of natural killer, or not natural killer, cytotoxic. H2 has the other name of, well, honestly, it's CD4, and that's one that has only been mentioned once by Laskew, I think. So this is information. You don't need to memorize these things if you don't want to. This is just if you hear someone, like if we have Laskew come in and ask a question, he's going to have a few questions on the exam. If he says CD4, you'll be like, what the heck? Oh, that's a T cell. So TH17 is also like CD17. CD can basically replace, I take that back, but TH17 is also CD17. And Treg has another thing, but I don't think we care about that one, so I'm not going to even do it. So, bunch of details. What you want to know is that TH0s are naive. They haven't had their DNA packaged for the last step for what they're going to specialize in. Okay? And then they become all these dudes. They're just slightly different T cells. And they're called T helper cells. And that's where the H comes from. So, yeah. Great. And natural killer cells, I just realized, are the one exception. They do go to innate. So there's one more innate cell.
Okay. So where in the innate line do they pop up, or do they just?
They scoot over. They come from the black sheep side of the family and just decide to go over and be innate.
Okay.
So this is where they come from, but if you remember, natural killer cells just go around and they check a cell and they check a cell and they check a cell and they don't need training. That's just what they always do. So really, it's B cells and T cells that are the adaptive, which makes it really easy. Is it a B cell and or a T cell? Then it's adaptive. Is it anything else?
Okay.
Then it's pretty much innate. There are a couple things that these also make. I guess I should put B cells end up making antibodies. And antibodies are the other important adaptive thing. Okay.
All right, so now did the natural killer cells come out of that grandpa's cell up there?
This one?
Yeah.
Yes, it did. And this is the common lymphoid progenitor. So myeloid half, lymphoid half. Common lymphoid progenitor. And it did come out of it, but remember, this is just packaging of DNA, and it just happens that the NK cell going this way makes so that it gets the proper packaging for what the NK cell's job is. And so it doesn't have to be split 100% between lymphoid and myeloid for innate versus adaptive. It just happened to go that way almost entirely. So what we know from this is that the natural killer cell apparently uses a lot of DNA that's similar to all the stuff over here, and so that's why it's on this side.
Okay.
But it's able to do innate, so upfront attacking. Anyway, so let's go ahead and close your eyes if you would. All right, and we're doing the innate again, innate. So it's the one that we started with.
The innate again?
Yes, we are. So what were your 3 clumps?
Okay, the monocyte makes macrophages and dendritic cells.
Great.
And then the next clump would be neutrophils, eosinophils, and basophils.
Great.
And then there's the cousins, which are the complement.
Great, and keep your eyes closed for a sec.
That's the innate side.
Yeah.
And then on the adaptive side is going to be B cells,
Good.
which make antibodies.
Great.
And then the TH0, which
Yeah.
then becomes TH1, TH2, TH17,
Nice.
or TH-reg.
Nice.
And then the natural killer cells are made from,
You don't need to remember where they're from.
they're made from the same one that those are, but it's part of the innate system.
All right. Great.
It's part of the innate system, or it's
It
part
is.
of the innate system and the adaptive system?
It's pretty much the innate.
Okay, so
Natural
it's
killer is
part-
innate.
Even though it's made out of the same cells the adaptive cells are made out of, it's actually part of the innate system.
Yeah.
Okay.
And so now you have answered your question of which system are we talking about?
Okay.
All right. So,
Now, who does what to whom and why?
oh, it sounds like Clue, doesn't it?
Uh-huh.
Okay. Who does what to whom and why? So, I'm going to erase this. Except for maybe some of these guys down here. That's pretty cramped. I think I'm going to expand that anyway. All right. So let's start with, B cells, T cells, and their story. Okay? So, a T cell. A T cell, well, stick to blue if that helps, since we're talking adaptive. A T cell, T sub 0, TH 0, T helper 0. Right now, a T0 has 0 things to do. He is just hanging out inside your lymph nodes. He's just hanging out, waiting until someone tells him what to do. He has 0 jobs.
Okay, so he matured in the thymus.
Yes.
And then just went automatically?
So the thymus is where so let's start with his birth. That's a good idea. Okay.
In the bone marrow.
Yes. So he was born in the bone marrow. All right? In the bone marrow, he does a whole lot of things that we don't care about. We just know that he was born there. And then he gets sent to the thymus, which is sort of a butterfly-shaped organ, which from anatomy we know is right here. Okay, so the thymus, I hated that in undergrad. I'm like, where the heck is the thymus? I had anatomy, but they never talked about the thymus, or maybe I phased out. I went cross-eyed. That happened. It's a thing. All right. So in the thymus, the T cells went through the gauntlet. All right, they went through some seriously difficult things. The thymus happens to have, and this is more than we need to know, this is just for conceptual stuff.
Right.
All right, in the thymus there is 2 parts. There is the cortex, which is the outside-ish part. And I'll put a wiggly line all the way around since it's... So between the straight line and the wiggly line is what I'm calling the cortex, okay? So it's the outside bit. And then the inside is the medulla. So some things happen in the cortex and some things happen in the medulla. In the cortex, I think is where, okay, so T cells, you know how they have receptors, right?
Okay.
All right. So they have receptors that are unique for a single antigen.
Yes.
Kind of like B cells. So there's basically, if you can think of those receptors as all right. Let's see. Let me make sure here. So the tips of those receptors right here can be changed in a lot of different ways. And so the protein sequence that goes into the tips of these receptors on the T cells is changed almost randomly. And there are so many T cells that you change, if you keep changing the tips to every possible combination, then you're going to have some things that can grab this shape, you're going to have some things that can grab this shape, you're going to have some things that can grab this shape. And eventually you make receptors that can grab virtually any shape, any protein, and those shapes, these shapes would just be different protein combinations on something else. So let's say that a bacteria had amino acids in this order, okay? Lysine, arginine, valine, lysine, lysine, and glutamic acid. And so it had those, and one more. You can tell how much I've been focusing on amino acids lately. Serine. All right. Those 7 amino acids are in a row. Those 7 amino acids, because lysine is lysine and glutamic acid is glutamic acid, just because of their natures, they're going to fold in a certain way. And so let's say that those 7 make a knot that looks like that. Okay? Well, these receptors scramble themselves up in such a way that every possible combination of proteins is going to fit in one or the other of them, because if you have random looking grabby bits, eventually you're going to have the right shape to grab any 7 sequence amino acid string. And that's why we can grab anything, including the Martian flu and all that stuff, is because bacteria use proteins and other things that also have shapes. And so eventually you're going to have something that can grab that shape. Now, in the thymus, when you make these random grabby shapes, what is considered a mature T cell is one that has been tested to see if it'll grab you. Because if it grabs you, that's bad. Then that would mean, because it kills whatever it grabs.
That would be like an autoimmune disease.
Yes.
Okay.
And so in the thymus, we have a little bit of every part of our body. We have cells that match every part of our body. We have like this library of just every different cell in the body. There's one for the T cells that they have to check against. Every single one of those cells. And if it grabs onto anything too strongly, all of those things are you. And then if it grabs on too strongly, something comes in and kills it. That's how we get rid of the self T cells. Yeah. And then there's some other jazz in there too. But they come out and they're Th0'd. Okay? They have no job. They have been cleared. And now they get to go into the lymph nodes. They get dumped out of the thymus into the lymph, and then they circle around, and it's what they do. And they spend most of their time in the lymph nodes. So they hang out. I'm going to go ahead and erase some of this so I have some more space. So they are now in a lymph node. This is kind of how I envision. Oh, that's not a lymph node. Just kidding. All right. Lymph nodes, sort of like a
Pinto bean.
Yeah, like a pinto bean. They vaguely remind me of the kidneys too. All right, so they hang out in there. Now, since they're going to be there and they know what self looks like, that means that if they ever attach to anything out here, it's a bad thing. So, kind of like them going and checking every cell in the library, other cells are going to come and bring, I found this. Is it good or bad? It's fine. I don't attach to it, therefore it must be self. If no T cells attach to it, because we've got a bajillion T cells. Because literally every T cell that didn't attach to self is okayed. So what are our antigens? Are you familiar with what an antigen is? Remember those 7 amino acid sequence thing that I drew up here?
Yeah.
That would be considered an antigen. It's just a shape made of stuff. Often amino acids. So an antigen is just a piece of something. And it's a piece that happens to be the size that a T cell can look at it. So, antigen presenting is when you're showing the antigen.
Right.
And we have 3 cells that make us super happy because they do. And that's not a memory thing, I just like them. So, 3 antigen-presenting cells. And these cells will go and scavenge stuff out and about, and they'll bring it up and say, hey, T cell, check it out. Those 3 things we will want to remember. So far we remember T cells. Now we're going to remember 3 antigen-presenting cells. They are macrophage, dendritic cell, and B cells. Okay? And these first 2 are the ones who are going to do most of the scavenging and bringing in. Okay? So let's pause for just a second once you're ready. And all right. This has a lot of conceptual stuff. So, all right. So go ahead and close your eyes. And remember, basically, you don't need to go into as much detail or whatever. What is the life story of the Th0 cell?
Okay. Th0s are born in the bone marrow, and
Bingo.
then they travel to the thymus, where they are put to the test to make sure they don't eat our own cells.
Great.
And then they are released to go to the lymph nodes.
Great.
And then there are antigen-presenting cells that will find things in the body and present them to the Th0 cell and say, is this good or is this bad? And those antigen-presenting cells are macrophages, dendritic cells, and B cells.
Great. Got it. You got everything. So, question for you. Macrophages, dendritic cells, and B cells. What is something that you can see that is a pattern? This is kind of a memory thing. What kind of pattern could you see for these two, say? You've seen those two together before.
They come from monocytes.
So you can remember that 2 of the 3 antigen-presenting cells come from monocytes. They're brothers. And that will remind you 2 things. Number 1, it'll remind you, 3 antigen-presenting cells, macrophages, I think it was dendrites. Oh yeah, well, they both come from the same thing. Okay, so yes, it definitely was dendrites. It's a double check. So now that you have that, and if you're ever going like innate, there was monocytes, macrophages, what was the other one? Well, I know that it was the other antigen-presenting cell. That means that it's either B cells or dendritic cells. I know B cells are over there, it's a dendritic cell. So now you have a 2-way double check by having that association and building in, just noticing when there's a similar pattern like that. You don't have to memorize that similar pattern, but noticing it gives you an extra pin in your little blackboard to keep the piece of information, keep the detail. So that's how you can, it really helps keep details in. The other thing was a B cell. Good job. Yeah, so you got it all. That's, all right. So, I'm going to go ahead and stop this video. Hopefully that was helpful.